When we talk about computers, we often speak as if there's just one kind. A CPU, some memory, a program, and a result. But that's a simplification we've all learned to live with. Underneath it, there are very different ways a machine can be structured, and those choices fundamentally change how computation happens. A computer architecture is not just about hardware. It's about philosophy. It's about where data lives, how instructions flow, and what the machine considers normal. Every architecture is an answer to the same basic problem: how do you move information and transform it efficiently? Some architectures dominate everyday computing, others exist on the edges, solving very specific problems, and some challenge our entire notion of what it means to compute at all. Let's start with the architecture that quietly shaped almost everything we use today. The von Neumann architecture is the mental model most programmers unknowingly carry around. In this model, there is a single memory that holds both instructions and data. The CPU fetches an instruction from memory, decodes it, executes it, then moves on to the next one. Data lives in the same place as the program itself. This design is elegant in its simplicity. One memory, one pathway, one sequence of operations. It made early computers practical, flexible, and programmable. You could change what the machine did simply by loading a different program into memory. That idea was revolutionary. But the von Neumann architecture has a flaw so fundamental that it has its own name: the von Neumann bottleneck. Because instructions and data share the same memory and the same communication path, the CPU is constantly waiting for the next instruction, waiting for the next piece of data. No matter how fast the processor becomes, it is limited by how quickly it can move information back and forth. Despite that limitation, von Neumann machines are everywhere. Most desktops, laptops, and servers still follow this basic structure, even if modern CPUs use caches and pipelines to hide the bottleneck as much as possible. The architecture persists because it's flexible, general purpose, and well understood. Harvard architecture emerged as a response to that bottleneck. Instead of a single shared memory, Harvard machines separate instruction memory from data memory. The CPU can fetch an instruction and access data at the same time, using different pathways. This simple change has profound consequences. It allows for higher throughput and more predictable timing. That's why Harvard-style architectures are extremely common in embedded systems, microcontrollers, and digital signal processors. When you're controlling a motor, decoding audio, or handling real-time signals, predictability matters more than flexibility. In practice, many modern systems use something called a modified Harvard architecture. Instructions and data are separated at certain levels, like caches, but unified at others. This hybrid approach tries to capture the performance benefits of Harvard while keeping the programmability of von Neumann. Both von Neumann and Harvard architectures assume something very specific. Computation happens in a sequence, one instruction after another. Even with parallelism, the conceptual model is still step-by-step execution. But not all architectures think that way. Dataflow architectures flip the model entirely. Instead of asking, what instruction comes next, they ask, what data is ready? In a Dataflow machine, operations execute when their input data becomes available. There is no global program counter-marching forward. The flow of data itself drives execution. This idea is incredibly powerful. It naturally exposes parallelism. If two operations don't depend on each other's data, they can run at the same time without coordination. In theory, Dataflow machines can be extremely efficient. In practice, they are difficult to build and even harder to program. Managing data dependencies at scale is complex. Debugging becomes non-intuitive. For these reasons, pure Dataflow machines never replaced traditional architectures. However, the idea lives on in modern systems. GPUs, stream processors, and even reactive programming models borrow heavily from Dataflow concepts. Another attempt to break free from the von Neumann bottleneck is in-memory computing. Traditional systems treat memory as passive storage and computation, as something that happens elsewhere. Data moves from memory to CPU, gets processed, then moved back. That movement is expensive. In-memory computing asks a radical question: what if computation happened where the data already lives? Instead of shuttling values back and forth, memory elements themselves participate in computation. This can drastically reduce energy usage and latency, especially for workloads like databases, machine learning, and graph processing. In-memory computing is still emerging, largely because it challenges decades of hardware design assumptions. Memory has always been optimized for storage, not logic. But as data sizes grow and energy efficiency becomes critical, this architecture is gaining serious attention in research and specialized hardware. Neuromorphic computing takes an even bigger leap away from traditional models. Instead of modeling computation as instructions acting on data, neuromorphic systems model computation as networks of neurons and synapses. Information flows through spikes, not instructions. Timing matters. Patterns matter. These systems are inspired by biological brains, not CPUs. They are incredibly efficient at tasks like pattern recognition, sensory processing, and adaptive learning. But they are terrible at traditional arithmetic and general-purpose programming. Neuromorphic chips are not meant to replace CPUs. They are meant to coexist with them, handling specific classes of problems where biological-style computation excels. Programming these systems feels less like writing code and more like training behavior. Quantum computing represents perhaps the most dramatic architectural departure of all. Classical computers operate on bits that are either 0 or 1. Quantum computers operate on qubits, which can exist in superpositions of states and become entangled with one another. Quantum architectures do not execute instructions in the traditional sense. They manipulate probability amplitudes. Certain problems like factoring large numbers or simulating quantum systems can be solved exponentially faster on quantum machines than on classical ones. But quantum computers are fragile, expensive, and extremely specialized. They do not replace classical architectures. They sit alongside them, solving narrow classes of problems while relying on classical systems for control, input, and output. What ties all of these architectures together is trade-off. There is no best architecture, only architectures that are well suited to certain problems. Von Neumann systems are flexible and general. Harvard systems are predictable and efficient. Dataflow architectures expose parallelism. In-memory computing minimizes movement. Neuromorphic systems mimic biology. Quantum systems exploit physics itself. When you write software, you are implicitly writing for an architecture, even if you never think about it. Your performance characteristics, your bottlenecks, and even your bugs are shaped by the assumptions the machine makes. Understanding computer architectures doesn't just make you a better low-level programmer. It makes you a better system designer. You start to see why certain problems are hard, why certain optimizations matter, and why no single machine can do everything well. Computers don't all think the same way, and once you see that, you start to realize that computation itself is far richer than a single model ever captured.